Looks like we can begin. Welcome back, everyone. So we're now working through week number 11, getting through the semester. The big thing coming up is next week, we're going to have our third exam. So this will be a week away from today, November 11th. If you've been testing in the classroom, you're in the in-person section. It'll just be another redo of what we did on exam 1 and 2. If you're in the fully online section, I sent you instructions on how to schedule your exam, either for the Pocatello Testing Center or Idaho Falls Testing Center. Well, any questions at all, folks, to start us out today? Okay, well, we're going to be moving through chapter 4 this week. We're currently in section 4.3. And 4.3 is pretty nice in a way because we're revisiting some older material that we've seen before, linear independence. We're going to combine independence with spanning and come up with a new concept, a basis. So the words here, linear dependent sets and bases. Bases is just the plural for the word basis, the new thing we'll be studying. Then sections 4.2, 4.3, 4.4, they're all kind of similar in certain senses. The way we're going to do the computations in there, they're not like section 4.1. So we're definitely getting over the hump in terms of the abstraction. But I think that's just about all I have for the announcements at the moment. We're going to start working through section 4.3. And as far as this third exam goes, it's going to start in section 2.2, matrix inverses, 2.3 using the invertible matrix theorem, and conclude in section 4.2, null spaces and column spaces. Well, any last questions at all, folks, before we get started today? Okay, just for off-the-wall comment, I don't think I'm going to draw a cooler letter E all semester. That's the best one that's come out so far. That was kind of weird. But let's get back to section 4.3. And here's that same definition. On face value, it looks pretty much identical from what we saw when we were doing this in section 1.7, I believe it was. It's been a while since then. Really, the major change is this statement. It's now a vector space V, whereas in the prior section, it was something like Rn or Rm. So it's a more general definition. It's a one-size-fits-all kind of definition now. But the equations are exactly the same, and so are the statements. We'll say that our set of vectors, V1 through Vp, in a vector space V, is linearly independent if this homogeneous equation, homogeneous because it's set to the zero vector, has only the trivial solution. So that's the same definition before. If it's not linearly independent, that would mean you can find a list of scalars, C1 through Cp, such that they're not all zero. That just means you have a non-trivial solution. And that's what this statement is saying. Linear dependence means you found the non-trivial solution to that same vector equation. So we're going to study this a little bit more, combine it with a new concept for a basis. And best way to study this is something a little bit different. We're going to look into this for the vector space P2. That's the space of all polynomials having degree at most 2. So here's two random polynomials, 1 plus t squared, non-factorable with ordinary real numbers. This one does factor, 1 minus t squared for P2. And we're wondering if this is linearly independent or linearly dependent. And there's more than one way to do this. If you've studied a weird object called the Wronskian before, you might know a pretty fun way to do this, and you're welcome to do that in this kind of problem if it comes up. Or just for the sake of working it through the definition, we'll just do it directly. And we'll do the Wronskian for another related problem at the very bottom of the notes, just for curiosity's sake. So to start this off, we're wondering if that is a linearly independent set. It means we write down the homogeneous equation. You can either use C1, C2, X1, X2, any set of scalars you like to write down with any notation would work out just fine. I'll write it out in the same notation they gave us. Let's solve. Let me try again. Let's solve C1. Instead of saying V1, because they're polynomials, we'll call this P1. And we'll throw in the input, P1 at t. So we're going to substitute in 1 plus t squared on our next step, plus C2 times P2 of t, set equal to 0. Where that zero is special, it's meant to denote the zero polynomial in P2. So we'll come back to that. Let's just put down a reminder. This is the zero polynomial, or we could have just said zero vector in P2. Now it just turns into an ordinary algebra problem. We'll substitute in what P1 of t is. This is C1 times 1 plus t squared plus C2 times, for P2, it's a 1 minus t squared, set equal to the zero polynomial. Now, to determine if we can get a non-trivial solution C1, C2, the strategy we're going to use next is the method of equating coefficients, which is probably something you've done maybe like in a calculus 2 setting. If you're using their, what was that called? The rational function decomposition theorem to integrate some weird wild polynomials, you might have had to have done this strategy already once before. The idea is we're going to distribute the scalars inside and then group all the terms according to their degree. So distribute C1, we have C1 plus C1t squared plus C2 minus C2t squared is 0. On the left-hand side, we can now regroup. The scalar portion, or the constant term, is just C1 plus C2. There's no degree 1 term, so we skip to the quadratic term involving t squared. Coefficient for t squared, after factoring, is C1 minus C2 t squared. And then we come back to the concept of this is our zero polynomial on the right-hand side. So because it's the zero vector or polynomial in P2, that zero on the right-hand side can be rewritten as 0 plus 0t plus 0t squared. And that's what every single vector in P2 looks like, just some choice for scalars across these 3 different terms. Finally, the equating coefficients means the only way 2 polynomials are equal, there's a quadratic on the left, a quadratic, well, not exactly because of the 0, but a polynomial on the right. And equality insists coefficients have to be identical. So we're building a system of equations out of this that now says C1 plus C2 is 0. The next equation is that C1 minus C2 equals 0. And there's a lot of ways to solve this. You could just use ordinary algebra, add up the equations, solve for C1, solve for C2 afterwards and by substitution. And you'd find that there's really only the trivial solution to this. But just for the sake of putting more linear algebra into this for kind of a review of methods, you could also break this down into the coefficient matrix. You could say for this system of equations, the coefficient matrix is, let's call it A. I'm not going to augment it. So what we mean by coefficient matrix is just the coefficients on the left-hand side. So it'll go 1, 1, 1, negative 1. And now we can discuss the uniqueness of the solution to this just by, well, doing a lot of things to this matrix. You could say, go all the way back to the invertible matrix theorem. That's going to come up in this section. Take the determinant of that matrix, that's part R now on the very bottom. If that determinant is not equal to 0, then that means this equation has at least one solution. Well, we want a unique solution. Hang on. You could go to, if the determinant is not 0, the fact that there is only the trivial solution. That's the better part D in the invertible matrix theorem. Notice it got a little bit bigger, so my parts are kind of out of order. Should have looked for that part D, though. It's in the same spot. So let's take the determinant of this matrix A. We can say since determinant A equals negative 1 minus 1, which is negative 2 and is not 0, by the invertible matrix theorem, this system of equations has only the trivial solution. So back to the vertical matrix theorem, it's talking about AX equals 0 having only the trivial solution. But we know we could turn this into a matrix equation if we like very quickly. That's the matrix right there. The vector X would contain C1, C2, and the right-hand side would just be 0, 0. So either way we look at it, we have only the trivial solution. And our conclusion is then, therefore, this set from the very beginning, P1, P2, is linearly independent. Because of this concept right here. So kind of just a refresher on the definition, slightly different algebra because we're working inside P2 this time, but same concepts keep coming up. Even if we're in the space P2, you can still make the invertible matrix theorem work for you once you get out a system of equations somewhere in the problem. But any last questions at all, folks, running through this refresher of the definition? Okay, so next we're going to combine linear independence with spanning. This is taking us all the way back to section 1.3, where we kind of laid out the ultimate objectives of the course. In that section, we defined linear combination, which was in turn used to define what we mean by spanning. Spanning is just the set of every linear combination. But if you combine that with linear independence, that's when we get the new notion, a basis for a vector space. So it's taken us a while to get there. Chapter 2, Chapter 3 had material that was kind of in a way not exactly related to a basis, but it led us to the vertical matrix theorem, so it was well worth that detour. So that's how the definitions combine now. We have, for the core definition of linear algebra, the definition of a basis, we'll say if H is a subspace of a vector space V, then a set of vectors indexed in the vector space V forms a basis for H if that set is linearly independent, just like we verified in the last problem, and it's also a spanning set for that subspace H. So that's what we mean by a basis. And the theorem that I skipped above right here is just kind of a refresher for other concepts of independence. We have a set is linearly independent if and only if it's not the zero vector, when the set contains just one vector. So this concept still holds for a general vector space V, like P2 or more abstract. If you have just two vectors, linear dependence means they're not scalar multiples of each other. And the moment you throw a zero vector inside a set, it's automatically linearly dependent. So sorry for skipping through that theorem. I forgot to put it there. We'll find opportunities to potentially use some of these ideas when we combine it with the definition down here for a basis. Well, our practice now is just to determine when we see a basis or not. Any questions or comments with the definition so far? Okay, one thing I would say about this definition when you really read it is it feels awkward. It feels like what the author should have done is give the definition for a vector space V and just fully delete this part. Say we have a basis for V right here, because that's kind of what we're doing down here in example 2. Our vector space is R3, and we're looking into the full vector space V itself right here. So the reason the author wrote the definition this way is it's kind of a one-size-fits-all type of definition. This definition will work if you're looking into a bona fide subspace, maybe the span of just 2 column vectors in R3. It also works if you're talking about the entire vector space V itself. So it's a very general definition in that kind of sense. It avoids the author for writing out 2 different definitions, a basis for a vector space V versus a basis for the subspace H. They're really the same concept. And another thing you can say here to just kind of justify why it's a one-size-fits-all is this other thought. For any vector space V, there are 2 kind of trivial subspaces. One of them is this one. The set containing the zero vector is a subspace. And another one that's kind of weird is V, if you track it through the definition of subspace, it's also a subspace of itself. It's just kind of the most uninteresting one. It's the whole space. But that definition allows for this. Also, V is a subspace of itself. Kind of a silly concept on that last one. Sometimes we have a notion that we like to throw in called a proper subspace, meaning your subspace is neither the zero vector or the whole set V itself. But taking this idea together, you can just allow the vector space V to be right here in this definition. So example 2 is kind of a fast problem. It's really more about just tracking through this definition, break down the moving parts to try to understand it better. But also, if you're going to define basis, this is a good one to start with. We've actually introduced this before when we defined the identity matrices. This is called the standard order basis of R3. Sometimes it's also called the canonical basis. Of R3. So it has several competing well-known names that we refer it to. It's not the world's best basis in every single situation, but for just a general nice basis, this is about as simple as it can ever get. So we're going to show that it's definitely a basis, and here's how we can start. Let A equal a matrix formed whose columns are just the basis vectors here, E1, E2, E3. But if that's our matrix A, we're definitely just looking at the identity matrix, because the refresher is that E1, it goes 1, 0, 0, E2 is 0, 1, 0, E3 is 0, 0, 1. And then a couple fast comments. You can determine independence just immediately for this set E1, E2, E3. We can say, since there is a pivot in every column of A, these vectors here, when we put them in a set, E1, E2, E3, is linearly independent. And that's a statement in the vertible matrix theorem as well. We have 3 pivots is another way to look into it. And so we have automatic linear independence. Then the other concept is, well, there's also a pivot in every row. So we can say, since there is a pivot in every row of A, pivot in every row means the column space of A, which is the span of the columns of A, or you could just have said span E1, E2, E3, however you decide to say it, it's equal to the entire space, R3 itself. So that checks independence, that checks spanning. And so our whole big conclusion here is then, therefore, that's a weird cursive B. Let me try again. B equals E1, E2, E3 forms a basis for R3. So that's the major ideas of what a basis is. We're going to resolve in the very next section, 4.4, what does a basis do for us when we look into coordinate systems? But any questions so far, just tracking through the definition? Okay, well, if you're really curious at the moment of what does a basis do for us, why do we care so much about spanning and independence? Here's another way to think about this. It's about the vectors of this vector space V. How do you write them down? Well, if you have spanning, what this is telling us is every vector in V is a linear combination of B1 through BP, these basis vectors. So that means there's a way to write down every single vector in the larger space V, just a scalar times B1 plus a scalar times B2 plus all the way down to a scalar times BP, the linear combination. So that's what spanning does for us. We can write down every single vector some way, somehow. And what does independence do for us? It tells us the representation is unique. There is only one way to write down that linear combination. There is no other way to do this. That's what independence does for us. Put both of those together, and the scalars that go in front of these are unique values. And that's what we're going to call coordinates in the very next section, and see some really interesting tricks in linear algebra once you have that notion of a coordinate system. So these are the two major ideas of a basis. Spanning and independence are doing different things for us. But at the moment, we're just studying what qualifies for a basis, what might not be a basis. So that's going to be our major problem we're going to look into on the next one. Kind of a big review problem in a certain sense. Any last questions or comments so far? Okay, so this next question probably kind of feels like deja vu in a sense. On exam one, we had a problem that was all about are certain sets of vectors linearly independent. On exam two, we had sets of matrices. We determined if they're invertible or not. Actually, that's going to be exam three. And for the final exam, there should be a problem like this one you ought to expect. I'll give you random sets of vectors, and you have to determine, do they form a basis now for R3? We just have to check two things. Are these sets of vectors linearly independent? And do they span? We have to justify our answers as well as we go through this one. But if it was an exam question, I probably would just say no justification necessary, just for a time saver. So let's go through these each in turn. It can be kind of tricky at first because if you look at these two vectors, these are linearly independent. That means this set of vectors might form a basis for R3. What would you folks say should be the ultimate answer? Is it a basis or not a basis?
Not a basis.
Yeah, I agree. If it's linearly independent and not a basis, essentially you're saying it does not span. And that's absolutely the case for just these two vectors. In order for this set of vectors to be able to span, we would have to be able to put it into a matrix, and that matrix would have to have a pivot in every single row. So the span of this is not R3. We can say this is not a basis. Since span 1, 0, 0, 0, 1, 0, it's definitely a subspace of R3, but it's not equal to R3 itself. Really, it's kind of a redo of what we did on this problem above. On the last problem, when you span the columns here, it did span all of R3 because there was a pivot in every single row. Try the same trick here, and we're just short of pivots. There's only 2 pivots in this particular matrix if we formed it from those 2 columns. So one thing that you might have noticed already is that number 3 is kind of special in a certain sense. We're going to later call that the dimension of the vector space. The dimension of Rn is going to be n itself. And in order to find a basis for something that has dimension 3, you really need 3 vectors to make that happen. This one was just too shy of vectors. But it's not just any 3 vectors. Those 3 vectors have to both be linearly independent and they have to span. So that's a problem with this one. Kind of the same concept as before, but there's loads of ways to answer this kind of question. When it comes to thinking about a basis, we go to this very same set of notes, section 4.3. So that's the section we're in. Notice that somewhere, part M, is the statement of basis itself. The columns of a matrix A forms a basis if and only if, through this invertible matrix theorem, A itself is an invertible matrix. So now, if we're dealing with R3, you have A through R different ways to look at what is an actual basis. It's kind of impressive in a way. So pick your favorite approach. Let's try using the invertible matrix theorem a bit on this one and vary our answers just to see it from different points of view. On this one, if we say let A equal 1, 2, 0, 0, negative 1, 0, 8, 9, 0, so the matrix A is formed from the columns in this set right here, then determinant A is automatically 0. We would do a cofactor expansion across row 3 is the sensible way to go. So that's the cofactor expansion. Expand that way. But if the determinant equals 0, we cite the invertible matrix theorem again. We're told that the columns of the matrix A forms a basis if and only if their determinant is non-zero. So the moment we got a 0 determinant, we go back up here and say this does not form a basis. So back to the set. The set does not form a basis for R3 by the invertible matrix theorem once again. Really, we can kind of just see it. The moment there's a 0 row, there's no way that's ever going to work for us. So let's take a look into the next one. Similar kind of concept, right? In fact, you could do the same exact thing. If you put this into a matrix A, then you could just, let's see here, transpose the matrix, and now you're looking into a 0 row if there was a 0 column. But because there's so much variety in how to answer this, you could also go, say, up on the notes just a little bit. To this theorem, we skipped across. And it says if the set of vectors contains a 0 vector, it's automatically a linearly dependent set. So that's a dependent set here by virtue of having the 0 vector. It means it can't form a basis because we lost that first part. The set is not independent. So that's another way to answer this one, just directly through the definition and through related theorems of independence. Since the set contains the 0 vector, it is not linearly independent. And so it is not a basis. So they're kind of fun problems in a way. You could row reduce some of these if you really wanted to, but the idea is try to avoid row reduction if you can, because there's almost always a faster way. Unless these were all just random numbers, 9 different random numbers, I might need to row reduction just to determine what's going on, or maybe take on a full determinant as well. Here's one from back in the day that you might have some remembrance of how this one might go. Again, you could row reduce this, and there's no harm done if you did row reduce it. Even in a real exam setting, you're going to get the right conclusion. But there's another viewpoint on this one. Anyone see if this should be a basis or not? Let me copy down the definition just for easy reference. Okay, so let's think of this set of vectors. What would y'all say to this one? Is it a basis or not a basis?
Not.
Yeah, I agree with you on this one. The moment you have this many vectors and they all have three entries, this is automatic linear dependence. So good call here. And this was a concept that was all the way back in section 1.7. Any set that contains more vectors than there are entries per each vector is a linearly dependent set. So same kind of problem as what we did over here in example 5. This was way back in section 1.7. The dimension's higher, but the concept's the same. There's just too many vectors in the set. So we can say, since there are more vectors than entries per vector, the set is linearly dependent and does not form a basis for the vector space R3. And I didn't mention the vector space R3 here. It might have been a good idea to say it. I set it up here as well. But it's good to just keep this in mind, whether you said it or not, because when we talk about the vector space R3, that's what this vector space V is all about right here. Your vectors in question, whether they form a basis or not, had to come out of that vector space V. In our problem, V is R3, which makes this last part down here a really very, very tricky part when you look at it. This is linearly independent. It's also a spanning set for R2, but the question was, is it a basis for R3? And it's automatically no, because the vectors didn't even come from R3 in the very beginning. So watch out for these weird problems like the last one on this set here. We can say this is not a basis for R3 since the vectors are not in R3. So it's a tricky one because, yeah, they are independent, they span R2, but the question isn't relative to R2, it's relative to the full vector space R3 itself. I think there's one last one to take a look into, but any questions at the moment? Okay, this one's not so bad to look into. What would you all say for this one? Is the last one a basis or not a basis? Any volunteers to finalize this one? Yeah, I agree. From the classroom, the justification is, or the conclusion is, it's a basis. And take your pick. There are many ways to justify this. Where's my section? Oh, here we go. Let's go back to the vertical matrix theorem for easy reference. You could say, geez, we've done the most of these, but let's use part C because we haven't used that directly in a while, just for variation. If you threw this into a matrix, the determinant's fast, it's upper triangular, it's non-zero, but also you're just kind of staring at the pivots, right? There's three of them automatically. So if there are three pivots and you're working with a 3x3 matrix, you can just come down here and say the columns of A forms a basis for R3. So let's go with that route, just for variety. Let A, hang on, let me put some space down here. Let A equal, if you ever want to do a shorthand, this would definitely qualify. Let A equal V1, V2, V3. V1 would be this vector, V2 would be this vector, V3 would be this vector. Feels like an abuse of notation in a certain sense. I didn't write an equality sign anywhere, but the author takes this approach sometimes in the reading as well. So matching with what the reading looks like, if you just say A is the matrix formed from the vectors here, we'll say Then A has 3 pivots. We can read them off. It'd be an echelon form immediately by the invertible matrix theorem. The columns of A forms a basis for R3. So I think that's our only second basis that came up. And again, a big takeaway for this is if you're working in a vector space like R3, we're later on in the very next section going to say the dimension is 3. That's the number of vectors in any basis. So if you see just 2 vectors or you see 4 vectors, those are automatic disqualifications. These cannot form a basis whatsoever. Well, that's practicing with the definition of a basis a little bit further. We'll look into more concepts along these lines of what if we really did have a subspace H? Maybe it's a column space or a null space or some other kinds of vector space. How do we find it or determine if we have a basis or not? Well, let's take a look into those very next problems down the line here. I guess before that, let's tie together this last concept here. Example 4 was meant to go along with this right here, the verbal matrix theorem. It's a list that just keeps on getting bigger and bigger. I think that gives us enough space. So this one, example 4, is kind of a short one, just a reminder that a lot of these things about bases can be resolved just through the invertible matrix theorem in this part right here. Ties together a lot of other stuff. The dimension of the column space has to be n. The null space has to be the trivial subspace, which means the dimension is 0, and we'll define what we mean by dimension very shortly. But for this quick example, it says, suppose A is an n by n invertible matrix, explain why the columns of A form a basis for Rn. We can just say the columns forms a basis by part M of the invertible matrix theorem. So the theorem will get even bigger in chapter 5, but that's when it gets its final size for this particular class. Example 4 is, again, just a reminder. It got updated in a pretty big way. There's now a lot of concepts being tied together, everything to date pretty much. Any questions at all, folks, with the example 4? Okay, so let's look into some new ideas so far. The spanning set theorem is a pretty big theorem that says a lot of stuff. So we're going to study this in a different set of contexts. It says, if you have a set of vectors, v1 through vp, in some vector space V, and you do this, H is formed in a very particular way. It's formed by just spanning those vectors. Notice that's half the definition you need to get a basis. Spanning is done. The other half is you want linear independence. But what the spanning set theorem tells us, if one of the vectors in S, say vk, is a linear combination of the remaining vectors in S, you can essentially delete that vector, and the set H is still spanned in the same way by removing that linear dependence. The set formed from S, by removing the offending vector vk, is still a spanning set. So that's a pretty powerful statement itself. It says next, if H is not the trivial subspace, then some subset of S is going to be a basis. We remove all the linear dependencies through part A, find all the linear combinations that some other vector could hold with the remaining vectors, delete them, and we keep shorting the set S until it's pared down to the point it is linearly independent, and now it's a basis. So that's the major idea with the spanning set theorem. Let's put this down below just for a quick reference on how this all goes together. So just one extra visual, because that's a brand new definition we're thinking about. We resolve immediately the spanning part. from the definition of a basis. So that part qualifies immediately. It says H is a subspace, and that might give us some kind of PTSD from section 4.1 because subspaces has 3 parts. There's a lot to check and think about. But the nice thing about section 4.1 is anytime you span a set of vectors, it's automatically a subspace. So that part is a foregone conclusion. So H is automatically a subspace of the vector space V. Spanning is resolved. And once we remove enough vectors so that there's no more linear dependencies any longer, this is the paring down part, the set that we're left with, there will always be some subset of S after we do all our deletions. It's going to be a basis. So somehow, some way, remove all the linear dependencies here. It's a basis for this subspace H. So it's a great theorem. It's a big theorem because there's lots going on here. It's interacting with the definition above. But here's one immediate and fantastic use of that theorem. The spanning set theorem gives us this as essentially corollary. The pivot columns of matrix A will always form a basis for the column space of A. So finding a basis when it comes down to a column space is just simply looking into the pivot columns. Every other column that's a non-pivot column is a linear combination of those major pivot columns. So we just delete them. We're left with a set A, S of just the pivot columns, and those will be the linear independence ones. So we want to find a basis for both the column space and the null space. We're using the definition, we're using the spanning set theorem, but here's what it all boils down to. We grab the pivot columns and we have a basis automatically. So that's an amazing theorem because it takes something pretty abstract, all this information here, and boils it down to just where are the pivots. So we're going to do both the column space on this one. We want a basis for that vector space we defined in 4.2. And at the same time, we'll find the basis for the null space, the new subspace we defined in 4.2 as well. So this one's in part review and in part finding a basis all in one. It's kind of a big problem. Any questions at all, folks, before we launch into it? Okay, for the sake of not doing tons of row reduction and copying a lot of stuff, the null space is actually the best place to start on this one. So let's begin solving what the null space is. We have to write down the solution set as a spanning set. That's because we're looking for a basis, and that's half the information there. Find your spanning set, and you have that part down. But once we do that, we're going to find the pivot columns of A, and that means we'll have the basis for the column space just automatically as we solve for the null space. So here's how all this work comes together. We'll solve. Let's first write down just what the null space is, just as a reminder. The null space of A, written as null A, is a set of all vectors X in R4, because there are 4 columns in this particular matrix, such that AX equals a 0 vector. That means we automatically take this matrix A and augment it with a 0 vector right here. This is finding the null space. So the augmented matrix will look like this. A augment with a 0 vector. That's tying together these two parts. Becomes 1, 2, 1, negative 1, 2, 4, 2, negative 2, negative 1, negative 3, 1, 1, and 1, 0, 5, 7. It's kind of amazing that no matter how abstract we get in chapter 4, row reduction always seems to make a comeback some way, somehow. So row 1 gives us a pivot here, and that means that's our first pivot column, just column 1 of the matrix A. Let's pivot off this, eliminate the entry 2 below, 1 below, and the negative 1 below. So first copying row 1, 1, 2, negative 1, 1, 0. Multiply row 1 by negative 2, adding to the entries below gives us 0. So negative 2 plus 4 for 0 again. Positive 2 minus 3 for a negative 1. Negative 2 plus 0, so -2, and then 0. Next, multiply by -1, adding to row 3, and we'll get 0, 0. This is going to be 1 plus 1 for a 2, -1 plus 5 for a 4, and a 0. Last operation is just to add row 1 to row 4, replacing it. We get 0, 0, and another 0. That's always nice. We're adding them together, so this one is now an 8 and 0. So it's getting pretty close in just that one operation. We have a pivot here. We skip column 2. Column 2 is not a pivot column. The column 3 is. Because there's also a pivot right here, this one is not fully in echelon form, but it's pretty close. We can already tell that's going to be a pivot column as well. It tells us that if you worked hard enough, you can write column 2 as a linear combination of those two columns. So delete column 2, and you're going to be able to form a basis for the column space of A. But let's keep on going because we're also doing the null space at the same exact time. Let's complete this row reduction because we need to get this to row reduced echelon form. And that 2 I circled is kind of curious. I should have circled that entry there. That's our next pivot entry. Let's multiply row 2 by -1, flipping these signs to positive so there's not as much copying. Copying row 2 gives us 0, 0, 1, 2, 0. Now we need to take row 2, add it up to row 1. We'll get 0, or hang on, let me try again. We'll get 1, 2, 0, 3, 0. Now pivoting off row 2 again, multiply it by -2, add it to row 3. We get 0, 0. So this will be -2, -4. So 0, 0 again. Last one goes 0, 0, 0, 8, 0, but you can just turn that into 0, 0, 0, 1, 0. So we're just about there. And getting a pivot where there's zeros completely to the left, completely to the right means 3 and 2 are automatically eliminated. They just convert to zeros. So the next step, this is row equivalent to, let's first do the row swap down below here. The 0 row with 5 zeros is now our row 4. This old row 4 is now row 3. Then we do a couple operations, eliminating this 3 and a 2. So the rest go 0, 0, 1, 0, 0, and then 1, 2, 0, 0, 0. Here's the part that was augmented again. And just to double check, pivot columns 1, 3, and 4 are what we have right here. So we're just about done. The column space of A is equal to the span of, let's call these A1, A2, A3, A4, just the span of the columns of A. But that means this column space is playing the role of the set H right here in that spanning set theorem. But once we've identified the pivot columns, we know that A2 is a linear combination of A1, A3, A4. So we can just remove A2, full on delete it, and it still spans. That's kind of an amazing concept. Now there's a subset of this set right here, A1, A3, A4. It is a basis. Because if we just delete this column, we're left with a matrix that has a pivot in every single column, forcing linear independence next. So that's how we get the basis through the spanning set theorem. But really, it's just what theorem 6 is saying as one overall punchline. Gather together the pivot columns in this matrix A, and you have a basis from the column space just automatically. So let's put this down as a conclusion. A basis for the column space of A is, it's actually tricky to write. Let's be very careful when we write this. It's so tempting to grab these reduced vectors right here after doing the row reduction. It turns out they're the wrong vectors, and it's a big surprise. When it says the pivot columns of the matrix A, we really mean the original matrix A, and that's the easiest mistake to make right here. We have to go to those specific pivot columns. So it goes 1, 2, -1, +1, -1. Then column 2 is a combination of the others. So go to column 3, -1, -3, 1, 1. And column 4, 1, 0, 5, 7. So we have half our answer. I'll put it in a box because our work is kind of all over the place with the null space being worked at the same time. That's kind of nice. Column space is done. Let's think about this for just a moment. What would have gone wrong if you grabbed these 3 columns instead? Well, you'd have to span this to get the entire column space. Column space is the span of the columns of A. But if you span these 3 columns here where the circles pivot, you'll never get a number in row 4, entry 4, because these are all zeroed out. Yet, the column space of A does give you a number in entry 4 because the entries down below here are non-zero. You can get a non-zero entry in the 4th entry when you span these 3 vectors as well. So we can see just by inspection, if we grabbed the columns from the reduced matrix, it's not the same spanning set. We're spanning something completely different. So theorem 6 is using the spanning set theorem very directly, and it gives us a basis just by finding the pivot columns of the original matrix A. That's pretty abstract already. Any questions or comments at the moment? Okay, we also want a basis for the null space, but this is kind of just a review problem, a redo of what we did in section 4.2 when we found a spanning set for the null space in the first place. So let's write down x1, x2, x3, x4. We'll solve the system ax equals 0 in parametric vector form by saying row 1 is just a statement that x1 is -2 x2. x2 is the free variable. That's where we had a column that was dependent, a combination of the rest. So we'll say that x2 equals 1 times x2. And x3, x4 are kind of interesting. They're both set equal to 0. So x3 is 0. And x4 is 0. So the null space is not a very complicated object on this one. We can now say x equals x2. We're now writing this solution set here in parametric vector form. It goes -2, 1, 0, 0, where x2 is in R. It also tells us something further. The null space of A is equal to the span of that one column vector, -2, 1, 0, 0. The reason I wrote that part out is notice the instructions are asking for a basis. This is not a basis because if you span this, there's infinitely many different vectors in there. You just pick a scalar and you multiply. That scalar is x2 and it can be any real number. So the whole set span -2, 1, 0, 0, this is linearly dependent. In other words, it's not a basis. If you want the basis, you grab just the vector and you lose the word span because span is giving you all of this stuff together, infinitely many different vectors, and there's only one basis vector. So to finalize this problem, we have to say a basis for the null space of A is this. It's a set, but it contains only one vector, -2, 1, 0, 0. that vector is automatically linearly independent, because if you have just exactly one vector and it's not the zero vector, you know by inspection it's linearly independent. That vector also spans the null space. That's what we wrote over here. So this is the basis vector right here. There's one really important comment that goes along with this. The process of finding the null space always, doesn't matter how many vectors we got. If we got several more vectors, that would have meant there's more free variables here. But if I got, say, 3 vectors, it is guaranteed automatically to be linearly independent. You don't have to check it out. If you did, you'd find that immediately. So this process of finding the null space always gives linearly independent vectors. So in other words, if you copy this process, finding the null space, no matter what goes here, to get the basis, you delete the word span, and whatever vectors you put in, it's automatically independent, so it's automatically a basis. So that's how we can find a basis for some subspaces, the column space and the null space. They're just different interesting tricks. The one for the null space is just going a step further beyond the spanning set and extracting the vector without the word span. Now you have a basis. Column space is trickier. You go to the pivot columns of the original matrix A. Those columns form a basis automatically. Well, that's a lot of stuff so far. Any questions, folks, on getting through this one problem? Really 2 problems in one. Okay, well, I have just a couple more problems to take a look into before we close out the notes. These are the main concepts that we're going to see in the homework and as far as exams would go on this kind of material. I felt like the problem that we just did is abstract enough, especially for the column space. We ought to do a do-over. So here's the do-over problem. I have a vector subspace H of R4. It contains 5 vectors, so it could be all of R4 potentially, but what we want to find is a basis. The moment we find a basis, we're going to know a lot more about this subspace H. Is it all of R4? Is it a proper subspace of R4? Is it dimension, say, 2, 3, or so on? What we need is a basis to determine all of that. Theorem 6 can be used here, even if you're not looking into a matrix A whatsoever. Call A is just shorthand for the column space of A, but you can force the column space of A here by just saying let A equal the column formed by these particular vectors. We'll reduce this matrix A, look into the pivot columns of that, and that'll automatically form the basis for H. So again, just kind of a do-over from before. Let's put down 1, 0, 0, 1, -2, 1, -1, 1. This will be our last row reduction problem for the day. 6, -1, 2, -1, 5, -3, 3, -4, 0, 3, -1, 1. The kind of unfortunate thing is that to make theorem 6 interesting, you usually have to have a pretty big matrix. So that's why they're kind of big out of nowhere on these problems. But it's fast to reduce. So we have a pivot here. That means we'll take that vector. Let's eliminate the entry below that one. So a lot of copying to start. 1, -2, 6, 5, 0. 0, 1, -1, -3, 3. 0, -1, 2, 3, -1. And here's the big operation. -1 times row 1 added to row 4 will give us 0. So this is 2 plus 1 for a 3. -6 minus 1 for a -7. -5 minus 4 for a -9. And 0 plus 1 for a 1. So we have a pivot here and here. That tells us already for a basis we have to take in column 2. So next, Let's eliminate those two entries and see what we get. So 1, -2, 6, 5, 0. 0, 1, -1, -3, 3. Add row 2 to row 3, and we'll get 0, 0, 1, 0, 2. Then let's multiply by -3 into row 1, adding to row 4. We'll get 0, 0. So this is -3, so +3 minus 7. -4 here. Multiplying by -3, so we have a 9 minus 9, so 0. And then let's see, multiplying by -3, kind of forgetting my operation here. That's a -9 plus 1 for a -8. I feel like I should double check my numbers on this one. Kind of lost the thread. Anyone see anything odd so far? Okay, I think I got it in. And this looks about the way I thought it was going to go. I believe it was 3 columns we're pulling. We have a pivot here, here, and here for sure. So it looks like 3 columns that we'd be pulling in. Looks like it's the first 3, but note it could be any 3 potentially, depending on how this was ordered. We're going to multiply row 3 by 4, add it to row 4. That's just going to give us a 0 row. So this is row equivalent, just to finalize it. 1, -2, 6, 5, 0, 0, 1, -3, -3, 3, 0, 0, 1, 0, 2. And now here's the 0 row. So we've identified 3 different pivots altogether. That means the last 2 columns, they're just linear combinations of the first 3. The spanning set theorem says you can full on delete them, and the set formed by spanning the remaining ones still forms a space H. So we delete those 2, we still have a spanning set, and the remaining 3 would correspond to having a pivot in every column. These are linearly independent. So the pivot columns of the matrix A, these 3 right here, forms the basis. So at this stage, our work is done. We can say, therefore, a basis for H is this set. 1, 0, 0, 1, -2, 1, -1, 1, and 6, -1, 2, -1. Well, that's another look into theorem 6. It's really just the spanning set theorem as one big paraphrase, the big punchline when it comes to dealing with a column space in particular. Any questions or comments at all, folks, running through this one? Okay, well, we've got one last problem for the notes. All of our spaces have been pretty concrete. We've been looking at subspaces of Rn essentially. So we're returning to one just like on example 1, where it's now a function space. This time we're not looking into polynomials, we're looking into pretty abstract space. It's going to be the set V, functions f. We're going to set the domain to be the entire real number line. So that means we don't necessarily know if these functions are guaranteed to be integrable. Just depends on what we put inside this set. Codomain is R, but the subspace H is kind of a nice one. It's going to be the span of these 3 trigonometric functions. So this is f1 sine t, f2 is sine 2t, and f3 is cosine t, cosine t. We want a basis. A basis does 2 things. It has to first span, so that part's done. Spanning is already qualified, so to get a basis, we just need a linearly, say what we need. We need a linearly independent set that spans H. Since this already spans H, we want to determine if this is linearly independent. Turns out It's not. One of these functions is a linear combination of the other two. Anyone spot which one it could be? Turns out, if you recall your trigonometric identities, it's all about that function. Use a double angle identity on sine 2t, and you could rewrite this one as f2 at t, which is sine 2t, can be re-expressed as 2 sine t cosine t, but that means it's 2 times f3 at t. So let's pull in the spanning set theorem to just get a refresher on what that theorem was saying. It's actually the biggest theorem of the entire note, so let's take another look at it. So this theorem has something to say. It says if one of the vectors inside your set S, which got spanned to form your space S, if it's a linear combination of the remaining vectors, F2 equals 2 times F3, so F3 is a combination of the prior vectors, then you can just remove that vector. Visually, this is what we've been doing. Remove it, and the set you get still spans H. So we found a linear combination. F3 is a linear combination of F1, F2. Specifically, we can say that F3 is 0 times F1 plus 2 times, or hang on, you'd have to divide that 2 over here to make it a 1/2 plus 1/2 times F2. So it's a linear combination. And now by the spanning set theorem, we can say, therefore, H is now equal to the span of sine t sine 2t. And this process by part B will terminate at the point at which some subset of S, the set, now becoming this set, will form a basis. It's now two vectors. And so if you can justify that sine t and sine 2t are not multiples of each other, that'd be a good way to end this problem. You'd know it's linearly independent, and then the whole problem ends. It'd be not too different from what we did right over here, looking into this, seeing if we can have a non-trivial solution. But there's a whole other way to look into this. That's going to be the so-called Wronskian. So we'll take a look into that, not as a problem that is necessarily going to come up in the homework or on an exam setting, but just as a related concept that connects these kind of function spaces together with linear independence. So the Wronskian is named after a very eccentric mathematician. So if you're curious, look into that guy. He was very interesting. It was named after him by some other mathematician some 70 years later, after he looked into independence of functions. It's named as a W of t. And what it is a determinant that goes like this. F1 of t, F2 of t, F1 prime of t, so the derivative, first derivative, F2 prime of t. And if I had three functions in this set, I would need a third row and have this second derivative filling out to the third row. So let's work it out to this Wronskian. It's going to be, well, f of t is sine t, f2 of t is sine 2t. Below, we're taking derivatives of just the entry above. So derivative of sine turns into cosine t. This one is a chain rule, so it's 2 cosine 2t. And in a real sense, this connects back to the good old invertible matrix theorem, kind of out of nowhere, because what we're looking into is, what is that determinant? If we can work this out and argue successfully that what we get here is not the zero function, then we can say that these two functions right here were in fact linearly independent. Same kind of logic as what we're seeing over here, connecting with independence. So let's work out this 2 by 2 determinant. This turns into Wronskian at an input t is sine t times 2 cosine 2t. So 2 sine t cosine 2t minus cosine t times sine 2t cosine t sine 2t. And now we need to do a little bit of algebra on this. What kind of function is it? Is it the zero function? Well, you could take w at 0. This would be cosine 0, which is 1, but sine 0 is what the thought I was thinking of. Sine 0 here becomes a 0. Sine twice 0 here becomes a 0. So w at 0 is 0. That's not good enough. This does not imply it is a zero function. For it to be a zero function, it would mean you get 0 at every single input. So let's try a different input to this. Take w, the Wronskian, at pi/6, just because it's an easy one to calculate. You would get 2 times sine pi/6 is a half. Cosine at pi/6, well, this is going to be 2 pi/6, so pi/3. Cosine at pi/3 is also 1/2. Here, that's a pi/6 for cosine, so a √3/2. Pi/6, well, twice it, that's sine pi/3, so that's another √3/2. So this becomes 1/2 minus 3/4, which is not 0. And so now we can make a big conclusion. The Wronskian at t is not equal to the zero function. That connects with the determinant being non-zero. And so we can say automatically this set is linearly independent. Therefore, f1, f2, the original functions here, which we called f1, f2, f3, before deleting f3, is linearly independent. And so we already knew it spans the set H. It's spanning again here after the deletion. It is a basis for H. So function spaces are kind of weird, but it's kind of nice to see there is kind of a connection, even with the Wronskian, on what we did with spaces like Rn. We just look at a slightly different kind of determinant to connect with linear independence. But any last questions at all, folks? Working with spanning set theorem once again on this one. Okay, this will be our stopping point for today. When we come back next class, we'll resolve a little bit better what use is a basis to us? What can we do with it? What cool facts and problems can we solve once we know we have a basis? And this last problem, really the big takeaway is the spanning set theorem itself. The Wronskian, again, was mostly for fun. It might have been something you've seen before. And it's probably something you're going to see shortly, if not already. But have a great afternoon, folks. We'll be back in 4.4 next class.